Hello everyone, this is Mohsen Saraj. I'm an application engineer from Azure Engineering Technical Team. Today I want to talk about another Flownex video which about pipeline and for transportation of crude oil. As you can see schematically at the bottom, we have oil tankers that we use the single point moorings before the marine terminals to collect the oil from the tankers, and then from these offshore terminals we will send the oil to the booster station that we have. It is like a pump station many kilometers inside sea to the onshore station, booster station, and after that for removing salt from the crude oil to the salt dome storage facilities that we have many reservoirs, for example 40 million barrels here. Pipeline, we want to have some improvement to the model. Suppose that you are a maintenance engineer that's supervising the pipeline, and first of all we want to use the crude oil material as a fluid material which is new to the system. It is not included into the library that you can use the video that I already created for custom material. uh, you can check that video. I have to create the new materials in Flownex. And the next part we want to see that what is the effect of ambient temperature on the flow delivery of the pipeline. We know that because of the pipeline in the depth of 35 meter of the sea water, so we can have different temperature along the pipeline, and if we add heat transfer elements to this to the pipeline, to the modeling the pipeline in a way that we can model the heat conduction along the pipeline and also thermal inertia of the pipe walls. We want to see that what is the effect of adding this heat transfer element to the pipeline system on the flow delivery and the temperature along the pipeline. And at the end, we want to see that what is the variation, what is the change in the pipeline capacity for the flow delivery, mass flow delivery, if we want to see that the offloading crude oil instead of 20 degrees Celsius will be at 60 degrees Celsius. Let's start with solving the problem. This is the schematic of the pipeline. I just extracted this from one of the Flownex tutorial about the crude oil pipeline. I created this from that tutorial and make it simple for the purpose of this video. Okay, this is the network, the fluid network, and you see that first part it is for single point moorings, and then we have the marine floating terminals, then pump station for booster pumps, and at the end we have the salt dome storage facilities. As you can see that we have the boundary conditions that it is dictated from the tankers and also the SPMs. 1500 kilopascal at the beginning, 1.5 megapascal, and the temperature is 60 degrees for the oil, crude oil. The elevation, as you can see, it is 35 degree in depth of the seawater, and then same depth of or elevation of the pipes. And here we go up 35 meter above the sea level for the terminals. So positive 35 at the next node, and then we have the pipelines that go down 35 meter below the sea level and send the crude oil to the booster pump stations elevation of 0, as you can see. So now we are on the land, and on the ground we have the pipelines that ended up to the salt facilities. For the pipes, we have this pipe on the land, as you can see, 40,000 meter, 40 kilometers, 1.2 diameter. uh, in the sea, we have the next pipe, which is 30 kilometers, and some other pipes that they are shorter. For example, this one, it is 70 meters length. This one, it is again 70-meter length. This is to 2500 meters, and this one again, this one 35 meter per second. And the diameter for these pipes 1.4, 1.4, 1.4, and after the marine terminals it is 1.2. So the first part is that how to add the new materials here. If we come here to the chart and look up tables, you can see that in the pure fluid, in the materials and fluid, I can right click and add a new category. This is what I already showed the details in the details in a separate video. I already add these new categories and call it petroleum, and then add a new pure fluid here that I call it crude oil. Double click here. I consider that it is incompressible. The density, it is 900 according to the tables that given for the material properties. Viscosity, it is a function, linear function of the temperature, so we have it in terms of equation polynomials that I added the coefficients for that. A0 2.6 2.06, and A1 it is negative 0.006. Conductivity, it is 0.06 watt per meter Kelvin, and heat capacity, CP, enthalpy, we consider it 2.5 kilojoule per kilogram Kelvin. So this is the setup how to add the new materials. And if you right click on one of the elements here and say that assign fluids, then here, as you can see that I already have it here, it is in the pure fluid. I use petroleum, the new category added here, and then it is crude oil. When I click OK, then you can see that in every element here in the network, pipe network, we have the same fluid. Here you can see, check here, okay, for a pump, next pipe, another pipe, pumping the booster pump, and even for the reservoirs. So having the added new materials, we can go and check the results here. We can solve the model here in at home ribbon, click run for the steady state solution. We can have it, you can see it here in the console. We see the details, and in the results for the temperature distribution, you can see that the temperature is around 60, a little bit below that, and 1 or 2 degrees above the 60 degree, and it is the 60-degree temperature that we have it at the beginning start point of the network. So almost very similar temperature distribution, which is not really true when we consider the effect of environment and ambient temperature in the sea and also onshore on the land. For mass flow rate, and you see that everywhere the same. For here, you can see the results that the total mass flow rate, it is 3456.57 kilogram per second, and the temperature it is 62.1331 degrees Celsius. And similarly for the temperature and pressure for the reservoir. Another way is to see the results is to click on the result tab, and here you can see the different parameters that Flownex calculated at the background. We have the flow delivery of the 3456 kilogram per second delivered to the oil reservoirs at the salt facility, and also the temperature here it is 63.2 13 before adding the heat transfer elements. So if we want to consider the effect of ambient temperature, we need to add heat transfer elements to model the this effect. Okay, for the second part, let's add the heat transfer elements. Come here to heat transfer, and we work with composite heat transfer. It means that we have different heat transfer mechanisms included into this element. We can come here, for example, and add a node upstream, nodes and boundaries. Come to nodes. Okay, so if you check the properties, what we need for the inputs for this heat transfer elements, you see that we have one part for the conduction and other parts for the inputs for the convection and radiation and other heat transfer mechanisms. Let's start with conduction. For the layers, we can click here to open the window for the layers, add a layer, click here, and for the thickness of the element in the direction, we can add, say that 0.05 meter. For the number of nodes, we can increase it to 3, and for the material data, instead of specify locally, we can go for select from data reference, and then click here to go to the metals and choose the carbon steel. So we set up the informations for conduction, click OK, and you can see here the information that we have for the layer. This is layer 0, we have this information. Now select the heat transfer element and the node, and have this here to be added to the pipe. So for the conduction area, we can say that it's from downstream's pipe area. So we're almost done for the conduction setup, as you can see, and then let's move on to other heat transfer mechanisms for upstream and downstreams. At upstreams, we choose convection, and the convection option to ambient, we use the same area as in conduction for convection 2, and also use the constant H or convection coefficient and the magnitude of 1000, and keep the ambient temperature at 15 degrees Celsius. We also set up the convection heat transfer for downstreams, same area as in conduction, constant H, and here now 60 watt per meter squared Kelvin for each downstreams. So we already set up everything's here for this heat transfer element. Conduction, the layer is here as you can see. Okay, and so the conduction and the setup for the convection upstream and also downstreams. Now we can add this heat transfer element to other pipes in the network too. Click C copy and here Control V to paste that and add this to this. Add the heat transfer element to this pipe too, and also add the heat transfer element to the last pipe. Yeah, so we almost done. As you can see, we have adding three heat transfer elements that we have. These are composite heat transfer elements that we have the setup for convection and conduction together. For the last heat transfer element, because it is connected to the pipe that it is on land, so for the downstreams we have to reduce this to 20, the magnitude of the convection coefficient, and the ambient temperature to 25. This is the only change for this heat transfer element. So we almost done, and now we can go and check and run the simulation. In the home section, run the simulation, steady state, solver, and see. As you can see here, we have the solution done. Console shows the details, and for the result layer, check the variation of temperature along the pipe that you can see, the pipeline. You can see that it is now for the last pipe before the tank reservoirs, it is the temperature from 60 degree, okay, now decreased to 30.943 degree, from 62 to almost 31 degrees Celsius, and the total mass transfer reduced to 30,004 kilogram per second. So these are the parameters that we can see. The total temperature almost 31 and the total mass transfer almost 30,000. So reduced from 3456 somethings previously we obtained to now 30,000 because of the effect of the adding the temperature ambient to the model. These are all for the temperature variation in the pipeline. As you can see, in the reservoir, now the temperature drops to 29.9. It used to be 61, 62 degrees. So now it is reflect better the reality, the physics of the problem. We can also check mass flow rate. For this one, again you can see that the total mass flow rate in as we already saw that, okay, almost 30,000 everywhere the same. But if we check velocity, it depends to the pipe diameter. So we almost done for the second part, and we could see the effect of adding heat transfer element to the piping system, that the temperature changes along the pipeline from high temperature of 60 degree to almost 30 degree at the end, almost okay here, as you can see, almost 30 degree. So you as a maintenance engineer can see that for this pipeline can deliver about 30,000 kilogram per second to the oil reservoirs here at the salt facility. The last part remaining is to see that if we change the temperature from 20 degree to 60 degree, that we will work on that on the next part of this video. Please watch the second part of this video. Thank you so much.